Hello everyone, my name is Timo Drick. I'm working for 7 Principles as an Android developer, and I will demystify pixel shaders with you together today. I live in Frankfurt, and I worked as an Android developer since 2010, I think. It's almost 13 years. And in this talk today, I will first do a short introduction to shaders, and then I will show you how to integrate shaders into Compose. And then we go into drawing simple shapes with shaders, and then animations. And at the end, I will show you a little bit how you can develop shaders, the process, and then a short summary. All my slides are also available in the internet, so you can scan this QR code, and this is a link, and there you have all slides. So you don't have to take pictures. So let's start. First, I will show some samples, what you can do with shaders. Here, it's one app. I used shaders for the background. So these triangles, these blurry triangles in the background are drawn by shaders. Or here is also a background drawn by shaders, these wave things. And here's one sample from the Google developers. It's one of the Jetpack Compose sample apps, Jetlagged. And here at the top, you see also a shader in action. It's actually is also animating. What else can you do? For example, you could do a shine animation at your button. Maybe this button is very important, the user should click on it. Or you can do a loading animation like this. It's also drawn by a shader. And yeah, I think everyone do AI development today. So, but when you develop your own AI, how can you visualize it? Maybe you can use a shader for this, like this. Anyone knows how this AI is named? Kit, yeah, you also know that. Okay, you passed the test. You can also go a little bit more crazy. For example, you can make the button hot by animating a fire, or you can do 3D animations for loading. It can also be used for transition animations. For example, here, this distortion of it's a normal Jetpack Compose UI, but it is distorted by a shader. So it looks like it's a certain, nowadays, I think every graphics pipeline uses shaders to draw everything. So also Android, under the hood, also uses shaders. And today my talk is about AGSL, Android Graphics Shader Language. And this is a new feature since Android 13. And there you can now program custom shaders using just the normal Canvas API. Maybe all of you know the Canvas API to draw circles, lines, and stuff like that. And maybe you also know shaders are used a lot in games, for example, but also on the devices, you can use shaders inside of with OpenGL, and also on iOS devices with Metal and macOS, also WebGL. So you can also directly program it in the browser. And one important thing about this shader, it's a completely different language, but it's compiled and executed on the GPU, so it's very fast. So maybe, you know this normal canvas draw operations, like draw a circle, and then you can fill it with a shader, and there are built-in shaders, like just using a solid color, or a linear gradient, a radial gradient, or maybe an image. And now this new function, this custom shader thing, you can now, instead of the built-in functions, you can program your own. And therefore, you have to define a function. And as input parameters, you get the x and y coordinate of the pixel, and you have to return the color. So the graphics card will ask you program for the color for a specific pixel. And of course, the graphics card will do this for every pixel which is visible on the screen. And the graphics card will also do this in parallel for every pixel, so it's very fast. Unfortunately, it's a completely different language. It's not Kotlin. So you see here a sample, this main function. Yeah, it's a little bit like C, but as a, yeah, maybe you know Java, so it's very similar. Here are some special types. Here, float2, for example, and then this record parameter. So this is the input parameter. And float2 is, yeah, you can imagine it like a vector with two components. And inside, you have this x and y coordinate position. And this float4 is a vector with 4 components. Yeah. And there you have to provide the RGB colors, and the fourth parameter is the alpha channel. So there you can define transparency when you want to have it a little bit that the background shines through. So you can set this to a smaller value. Also important, this parameter with this struct code, you get the pixel position. Yeah, it depends, of course, in my samples here, it's this rectangle at the bottom is 200 pixels width. So the x and y coordinates are in pixels, and you have to return the colors in values between 0 and 1. So 1 would be, in this case, 1 for red means that the red channel is fully saturated, and the other channels for green and blue are 0, so there's no green and no blue. And 1 for alpha, so it's completely non-transparent. So now when we want, of course it's boring to have just one color. So now when we know we are 200 pixels in width, so we can use the x coordinate, for example, to define the red color channel. And in this case, I divided this x coordinate by 200. So this means when I'm on the right side of this rectangle, then it's exactly 200, and 200 divided by 200 is 1. And on the left side, it's 0. So just that you understand a little bit more, this is data type, float2, for example. Here you can provide 2 parameters, x and y. There's also a float3 with 3 parameters. It is x, y, z, and a w if you have 4. It's also possible just to use the same data type for colors, and you can also access this with different accessors, like .r for the red, and .g for the green part, and .b for blue, and .a for alpha. So it depends what you are doing with this data. You can use both. But we can still use, also, when it's color, you can still use .x, the same. So now how to integrate it into your compose code. That's very simple. First, you can, for example, just put the shader code into a string variable. Also in Android Studio, you have the option to have this add language annotation. And then Android Studio will also do some code highlighting inside of your string. So it's very nice. And then the compose part itself, you can, for example, define a modifier. In this case, I call it background shader, and provide the shader source as a string. And then use this draw with cache function. This is a function from compose to draw with canvas, draw operations. And now this new thing, since Android 13 is the runtime shader, you have to create an object out of it and then make a brush out of this shader. And this brush you can then use to draw different things. For example, here in this onDrawBehind function, I can draw a rectangle. In this case, when you do not provide the width and height or position, then it will draw the rectangle full screen and uses this brush as a color to fill the rectangle. And this is then your code, your shader code. For example, here, when you integrate this into your composable screen, then you can just use a box, for example, and then use this background shader as a modifier. And here, just to show some sample, I did a button above this, and then the application would look like this. So it's now just this red color. Now when we want to have this gradient also, yeah, we don't know the size of our rectangle, so we have to forward this to our shader code, and therefore you can use uniform variables. So here I use this variable named uniform size and from type float2, so it's x and y coordinates. And in your compose code, you can then just call this shader.setFloatUniform. And there you provide the variable name, and when it's a float2, you have to provide two parameters, two floating point values. Yeah, and then it looks like this. Yeah. Okay, so yeah, a little bit boring just to do gradients, because then you can just use the built-in shaders. So let's see how we can draw simple shapes with this. And to be able to draw a shape, when you only know your pixel coordinate, the x and y coordinate, you need a distance function to the outline of the shape you want to draw. So yeah, from the graphics card gives you the actual pixel position, and you have to know how far away it's from the outside. And when you are inside of the shape, you can draw a different color than when you are outside. So inside would be 0, or the distance would be 0 or smaller, and outside it's bigger than 0. So yeah, let's start with a simple distance function. The simplest one would be to draw a circle. And to draw a circle, I only need to calculate the distance to a different point. So it's just the vector length between the both points. Yeah. So in this case, and also, I mean, maybe you know Pythagoras from school, but you don't have to program it directly because there's a built-in function in shaders. It's called length, and there you can calculate the length of a vector. So let's assume our canvas is 200 by 200, and we want to draw the circle in the middle. Then, yeah, I set the circle position to 100, 100. The radius I also set to 100. Then when I want to calculate the distance, I just use this length function and subtract the circle position from the frect coordinates so that it's exactly in the middle. And I don't want to have just a point, so I subtract from the distance the radius, and then I get a shape that exactly have exactly the radius of R. And then I can just do a if-else branch here, depending on the distance, if it's greater or smaller than 0, and provide two different colors. In this case, black when it's inside and white when it's outside. When you look closely, maybe you see that the outline of this shape is now very edgy or pixelated. So you see the pixels. Therefore, often in shaders, this smooth step function is used. So you can define a start and end value, and the smooth step function will then smoothen the, so that you do not have a step between these both values, and it will start slowly and end slowly. You can input any value, and the output would be a value between 0 and 1. Also, we need the mix function, and this function, it's very simple. It's just do a linear interpolation between two values, between value A and B. And the third parameter, weight, it's also a parameter between 0 and 1, and there you can define how much you want from A and how much from B, and it will just linearly interpolate between. The smooth step is not linear, but this mix function is linear. And now back to our code. So when we now build in the smooth step function, here I define the size of this edge as 20, for example. And then in line 7, you see I use the smooth step with starting at 0, the distance of 0, and then goes to S, at 20 in this case. And then I provide just this distance value. And now we have this this value, the smooth stepped value, as I would say. I subtracted this S from R, because otherwise the circle would be greater than our canvas. And now I have also two colors, background and foreground, and I can use the mix function to smoothly go from the background to the foreground. And in this region where the smooth step function kicks in, you don't see pixels anymore. It's more a little bit blurred. You can also increase this when you set S, for example, to 90, then it's very blurry, or you use a smaller value, then it's more sharp. You can reduce it more, but then at some point it gets pixelated again, so you have to try. So, of course, there's not only functions for circles. There are a lot more. So here just some samples of box, triangle, hexagon, and pie shapes. And Inigo Quiles has a very good website, articles about this distance functions. Not only 2D, also 3D, but for our case, 2D is enough. So this are the basics, the simple shapes. And now you can also combine shapes. For example, when you want to do a subtraction, so you subtract one shape from another, you can use the max function, but you have to provide the distance with a minus for this distance or this shape you want to subtract from the other shape. So it just takes the maximum. But of course, when it's minus, then it's inverted. For a union, so when you want to have both shapes together, then you can just use your minimum function. So it will take the minimum distance from both shapes. Or when you want to have an intersection, then you can just use the max function without a minus for any shape. So very, very simple functions. Other things you can do with, you don't have to change the distance functions, but when you, for example, move your shape, you can just move the coordinate system in the opposite direction. Maybe you can also think of this coordinate system like the universe. In our case, it's just a 2D universe. and you move the universe to the right, and then the shape will move to the left, yeah? And you can do this just by plus, equals, and then you can provide a vector, for example, with x and y coordinates. You could also multiply these coordinates, so you scale your universe. When you want to get your shapes bigger or smaller. Here is a sample. So first, I move the coordinate system to the center. So this means that my 0, 0 coordinate is exactly in the center of my shape. And then here, for example, I multiplied the x-axis by 2, and this will shrink my shape in the x-axis, or in the horizontal axis. And when I multiply the y-coordinate by y-axis by 2, then it will shrink the y-axis. So maybe you think it would make it bigger, but actually it makes smaller because you deform the universe around the shape. You can also do rotations. Here's a rotation matrix, 2 by 2 matrix. You don't have to understand this code, this mat2 is also a data type, and there you have to provide 4 different values, and it's a 2 by 2 matrix, and interpreted by 2 by 2 matrix, and then you can use this matrix and multiply it by a vector, and then you get a vector back. And in our case, I use a box now as a sample for the shape, because when you rotate a circle, nothing really happens. So here's a function. It's also from Inigo Quiles, a function for the box, or a rectangle, and then when we use this, first I move my coordinate system to the center, and so that I have 0, 0 in the middle of my shape. And then when I, for example, want to rotate it by 45 degrees, I first have to convert this angle into radians with this formula, and then I can just also multiply this frac coordinate, my coordinate system, by the rotation matrix. And then I calculate the distance using just my distance function. I can use also the smooth step to smoothen the edges of this shape. Okay, so now, I just showed you some basic things, and maybe you will think, it's very boring and you cannot do really interesting stuff with this. But you can. So this, for example, is I only using triangles and rotate them a little bit, scale them, play around with the smooth step range a little bit, and color, and use different colors, and then you get amazing effects. And it's just, it's not so much lines of code. Here I define this triangle function where I can define parameters like angle, radius, and stuff like this. And then I just apply this to my shader code. And that's all code you need for this background. Okay, so next topic, animations, how you can do animations with this. So let's implement an animation shader. Now, I use also a modifier here, but I use this keyword composed to be able to have animation values here. I use just normal compose animation functions here. This remember infinite transition is from compose, and I define this animation. Here, the important thing is it's an infinite animation, And I can define an initial value and a target value, and I define it, the initial value as 0 and the target value at 1, because then inside of my shader, the math is a lot easier to do. And also I define here the duration, and it's 2 seconds. And important, this easing function, normally it's not a linear function, so you have to set it to linear easing, otherwise your time axis will be distorted, and or maybe you want this, maybe not, it depends. But in my case, I do not want this. And then, I use the same function again with this draw with cache. And we already know this float uniform thing to provide values from your compose code or Kotlin code to the shader. So I define now a uniform called iTime, and then I can use this animation value, and it will be forwarded to my shader code. Yeah, let's see the shader code. As I said, I use this uniform iTime here. I define it in the shader. It must be called the same, yeah. And then it's the same code like before in the non-animated version. And here now I multiply the angle by iTime. And in radians, pi times 2 is exactly 360 degrees. So this means when I multiply this by 0, then it's 0 degree. And then by 1, it's exactly 360 degrees. So this means that I have exactly one rotation, one complete rotation after one animation cycle is done. Yeah, just with this knowledge, you can also do a little bit more fancy stuff, like this animation I showed you in the introduction. Yeah, of course, the code is a little bit more complicated. And also when you program these shaders, often it's convenient to convert the coordinate system so that it's that the middle or the center is 0, 0, and the left side is 1, minus 1, and the right side is 1, and top is 1, and bottom minus 1. So then I don't need to change any code when the size of my canvas changes. It will automatically adapt to the size. And the math is easier. Here, this is the same angle calculation like before. And now in this case, I just wrote a for loop. And in this case, I draw 24 rectangles, but I do not rotate the rectangles. But I just changed here the size of the rectangles and the smooth step function, depending on my current animated virtual angle. So I move the rectangle a little bit outside of the center, and and then I calculate the distance depending on the angle and the intensity also. And here it's just this normal distance function for a box. Also, I use the smooth step, and when it's greater, I use a more blurry version. So that's all of the code. I use this float L value for luminance, so I add up every rectangle, just add it, and then I clamp it to between 0 and 1. Otherwise, it gets a little bit overexposured. And I can, when I now, this is just a value. And now I can multiply this value by the color I want to have. For example, in this case, it's green. And then I can return this color. Oops, sorry, yeah. Okay. So now another example I showed you, this shine animation. For this, I do not need any rotation at all. I do the same like before, but in this case, I multiply the y coordinate by different values than the x, and then it's a little bit tilted to the side. And in this, and then I use a smooth step function for the starting edge of this highlight and subtract the smooth step of the end edge from it. Yeah. So it's just two smooth step functions. And then I can just also calculate the color out of it. So it's just under 20 lines of code to do this animation. Yeah, of course, it's shader code. You need also a little bit in your compose code. I showed you already this animation, and when you look closely now, it's just rectangles and circles. So you should be able to implement this now with the shader, yeah, with this knowledge. Here's the shader code for this. I don't want to go into details, but it's also just smooth steps, circle, distance calculations, and stuff like that. On end, it's just 31 lines of code. Okay, so how can you start now developing? The good thing is in Android Studio, you can just use this live coding support from, you know it from Compose, so when you change some code, then instantly you see this on the device, also the changes. But when you change the shader code and you did some mistakes, then this will crash the app. So maybe you should put a try catch around this runtime shader creation, because the compilation will fail and then the app crashes. So I only draw this when there's a valid shader. One other thing, as I said, to use these functions, or this runtime shader function, we need at least Android 13. But the good thing is it's also supported by Compose for desktop. I'm not sure about iOS support, because I do not have a Mac, cannot test it. But I think it should also work on iOS, because it's based, this AGSL is based on SKSL. It's the same. I don't know why Android renamed it. They have their, I think because maybe they want to later change something internally, but yeah. And SKSL, it's Skia shading language. And Android uses Skia to draw everything. It was not so hard for them to support these custom shaders. It's also supported in legacy UI, so when you're still using this old view system, it's also supported there. And SKSL itself is based on GLSL, which comes from this OpenGL shading language. Yeah, it's a long time around, so almost any Android device supports OpenGL, even very old devices. I think the G1 device also supports OpenGL, but only 1.0, and this is you cannot do custom shader programming. What about backward compatibility? So normally you have to support older devices in your app. One solution would be that you check if the SDK, the version of the SDK is smaller than 33, then you just provide a solid color, for example, or some built-in shaders like the linear gradient or something like that. There's also another solution. It's a little bit limited. So, as I said, OpenGL is supported on almost any Android device, or even very old versions. I programmed a little OpenGL shader. It's just an experiment, so it's not ready for production, but I just programmed some OpenGL code and then convert the AGSL shading language a little bit so that it will be executed then inside of OpenGL as in GLSL shader. on a rectangle. But then, yeah, you are not free to draw anything with the canvas anymore. But when you just want to show the whole screen or a rectangle on the screen, I'm using a texture view or a surface view for this, so it's a little bit more overhead. But in theory, you could also get this running on older devices. Okay, so now at the end, I will show some more inspirations. So some experiments I did. For example, here, you can do also 3D. And here, for example, I changed the position of the sun depending on the device position in space. So when I turn the device, the shadow will move. Or when you have an audio player, when you program an audio player, you could do a visualization of the spectrum like this. It's also drawn by a shader. Yeah, one new thing in my slides now. I just, 1 week ago, I thought, what are also simple shapes and can be drawn? Yeah, this Android mascot, how it's called again? Maybe Backdroid, yeah, we learned in the quiz at the beginning. Yeah, that's a little bit boring, but they have a new design for the Backdroid, and it's in 3D. And this I also, I tried to create it with a shader. But 3D is a little bit more difficult, but in theory you could just do the same. So you also use distance functions, but you have to program a little renderer around it. Yeah? And also you come to the limits of AGSL, then maybe it's better to go to OpenGL. So, just a short summary. So we saw that you can do amazing effects with AGSL. And when you use it, yeah, your app would really stand out because not many apps use it nowadays. But of course, yeah, it's a steep learning curve, so it's a complete new language. But keep in mind, it's just for the visualization, so it's not a lot of code. You do not have the business logic in this code. Yeah. And important, it's very fast, so it gets compiled. It's not a JVM thing or something like that. And it's directly executed on the GPU. But yeah, when you just want to draw simple shapes which are not fuzzy at the edges or something like that, then maybe it's better to just use the canvas draw operations. It's a little bit simpler. Yeah. Okay, so here are some references. I have everything I showed you today. I have sample code for this. I also wrote some articles in Medium with a little bit more details, so you can look into this. Yeah, and another thing is there are a very big community which do this shader development. I can recommend the channel from Inigo Quiles. He has not only an articles, he has also a YouTube channel, and also the Art of Code. It's also a great YouTube channel. And there's this website, shadertoy.com, and there you get, you can just open it and then you see amazing shaders, also in 3D and 2D, everything. And you also see the source code for everything. Okay, that's all. Thank you for your attention. Here again, this QR code, or you can also type in the URL and my contact. So, thank you very much, and yeah.